A very warm welcome to this section. In the next few slides, we will focus on section 1311. They're all color-coded here in this blue. And the focus is on sulfur compounds. There are two main classes that are first covered, thiols and sulfides. I also want to give you a heads up and a reminder as to what's significant once we integrate sulfur into the structure. Remember that in main group number 6, we first have listed oxygen, then we have sulfur, and then underneath selenium. But we will focus on these two here. Sulfur can often take the place of an oxygen and vice versa. When we do that, here you see an alcohol example, a 1-butanol derivative. Once we replace the oxygen with the sulfur, that becomes a butane thiol derivative. So many sulfur compounds are analogous to alcohols, or this SH group, this thiol group, analogous to ROH. And this is the substitution we make, as I had just pointed out. Now, a long time ago, these compounds were also called mercaptans. It had to do with the fact that sulfur easily bonds with mercury, and so we could use sulfur compounds to clean up mercury spills, including in the laboratory. We used to use mercury thermometers, and once they break, they can spill all over the floor. But sulfur can actually help bind and clean up that spill. Something else I want to point out already is that we have only s and p orbitals for oxygen compounds. However, sulfur is often an exception to the octet rule because it has s, p, as well as d orbitals, and these additional d orbitals can allow it to hold more than 8 electrons. So the mercapto prefix was used a long time ago, and we can utilize it as a substituent. Here are a couple of examples. Note that the alcohol is getting the highest priority, so we would name it or start numbering on the right-hand side, 1, 2, 3, 4. And then you come up with this mercapto substituent in the 3 position. When we are looking at the compound below, again, the alcohol has the highest priority. So this is our 1, then 2, then 3. And now we have a 2,3 indicator for these two groups. And then here, this compound has been used to treat mercury poisoning. So, thiols are actually known for their really bad odor. Unpleasant is a kind word. They downright stink. Skunks use these thiols as a defense mechanism. Methane thiol is actually used to natural gas. So natural gas itself cannot be smelled, but if there's a leak, you have low concentration of this, which can easily then detect whether there is a leak in the pipes. If we were to look at these structures, so methane thiol, so methane is derived from CH4. Okay, and then if we have methanol, that would be CH3OH. And then methane thiol would be your CH3SH. Also an important aspect as we are looking at various transformations, make sure that you understand where the non-bonding electrons are. And oxygen and sulfur compounds do like to be divalent, but sulfur can have more electrons, so we see other bonding patterns. Note that hydrogen sulfide ion, an anion, is a strong nucleophile and a weak base. So it can be utilized in lots of SN2 reactions, but we don't typically see an E2 reaction when that anion is present. Again, for mechanistic understanding, and mechanisms are our friends to understand how the electron flow goes to account for reactivity. You may want to draw a more detailed structure, a Lewis structure showing all the electrons, and now here we are and have a negative charge. So here's your hydrogen sulfide anion. On this slide, we are focusing on a couple of SN2 reactions using NaSH. Understand what this represents. Clearly, this is an ion pair. We have Na plus, and then we have SH minus. You can represent this as dots or as lines. Lines are faster, right? So if I draw this with lines, this would equally be accepted in your work on worksheets, for example. So we now see that this has nucleophilic characteristics. This is a typical SN2 reaction, attacking the delta partial positive charge next to the halide and then breaking that bond to bromine, thus giving us this thiol. Also note that when we have stereochemistry, that this happens with inversion. Down becomes up, and in this case, up becomes down. There are ways for oxidizing compounds. We can use two thiols and put them together and form this disulfide bridge. Note these reaction conditions. They are basic. And so in the display that I pasted from the publisher, there's a little, there are some issues here. So there are a couple of symbols. This should be a plus here, and we forget about this. I'm sorry, this should be a minus. Those symbols are a bit distracting. This should be a minus, and this should be a plus. And that's also true for this molecule here. That's a little bit wonky. So this is plus, and this is actually minus. And I prefer you put a circle around the charge to make it very obvious that this is a charge. Analyzing these conditions, so we have here ethane thiol under basic conditions. So NaOH means that OH minus comes in and picks up that proton. Okay. Then we get to this structure here, which I've also shown here. So here's another representation, and we can fill in all the electrons. So this now makes for a good nucleophile that will attack bromine. Basically, it's a net Br plus addition, attacking one bromine, breaking off the bond to the other bromine. So that's exactly what's shown. What's then shown here as a product. And then we can have a second molecule. So let's just do this. So we have S, Br, and then we have a second molecule coming in, S minus. Again, draw these electrons to understand the nucleophilic characteristics. Now this can displace the bromine, and there you are, and you have your disulfide product. So that's for this example here, and here's your generic outline. SN2 and SN2 is what's being applied here, of which you learned a lot in Orgo 1. We can also take a disulfide bond and reduce it. We're utilizing zinc metal. This is a reduction. Sometimes you just see either an R or an H, as we tend to increase the bonds to hydrogen. So we're replacing two sulfur bonds with SH bonds. So that's a reduction. They can occur via a free radical mechanism. But I think what's more important in understanding the dynamics here is that we see quite a few sulfur-sulfur bonds in proteins. And this bond can easily be broken. It's only about 53 kcals per mole for the bond dissociation energy. So dissociation meaning breaking apart. And that actually influences the shape of proteins. And in fact, that is what's being manipulated when one perms hair. So a perm in hair, first the disulfide bridges are broken, new shape is assumed, and then so once they are broken, they have SHs, we're changing the shape, and then we're doing the reverse and oxidation, and then lock that shape into place with disulfide bonds. All right, so sulfur analogues are of ethers are also possible, and they're called sulfides or thioethers. So here's diethyl ether, ethyl-ethyl. If we just swap out the position with the sulfur, we call it a sulfide. We can also utilize terminology we've encountered before, for example, alkoxides. We can now indicate a substituent. Here the substituent is a methoxide. When we replace that with a sulfur, then it is a methyl thio group or substituent. And you have a couple of examples with the names listed below. Generally, we prepare sulfides through, again, an SN2 reaction, as we have learned here, and that's why it's important to draw Lewis structures. Again, this is delta plus, this is delta minus. These are all your SN2 reactions from Orgo 1. We can now make a new bond, and here we are with that product. Recall that thiolates are formed by deprotonating a thiol with sodium hydroxide. So this should be a bi. And we can formulate that as such here. So we go from here to here, and then we need a strong base to make that anion and strong nucleophile. So in this slide, a couple of other aspects. We can now utilize these sulfides and do additional reactions. What you see here, for example, is that we have one of the lone pairs here that can do an SN2 on a methyl halide. Note that these are highly reactive compounds. They're actually quite toxic because we're full of nucleophiles, and so we can methylate DNA and other components in our body that can have adverse health effects. But synthetically, we can manipulate that. Methyl iodide is one of the strongest reagents and dangerous reagents to work with. So this is a methylation reaction where we're adding an S-methyl group. Sulfur here carries a positive charge. So we say that these are now, this molecule here, this is a strong alkylating reagent. And that alkylating reagent can then add with other can react with other nucleophiles. That includes DNA. Okay. Now, we do know that there's some real-world application here. You may want to look up and read the sections on SAM-E, which is a natural alkylating reagent that you can find. But basically, this now becomes a delivery system for a net transfer of CH3+. CH3+. CH3+ itself is very unstable. You've learned that. You've learned that methyl cations are the least stable, less than primary, less than secondary, less than tertiary. So we kind of have an intermediate stabilization in these compounds. Sulfides can also be oxidized to two more classes of compounds, sulfoxides and sulfones. Here you see the square brackets for indicating oxidation. Different reagents are used to either go from here to here or to go directly from here to here. Notice that subsequently a lone pair is replaced with a double bond to oxygen, and then here an additional lone pair has been replaced with a double bond to oxygen. So what kind of oxidizing reagents do we use? That's shown on the next slide. We use compounds like sodium metaperiodate, which is shown here. So you see that this then stops here. There is a lone pair still here. And we basically, here also it shows you how to name these compounds. So we're listing the substituents, a methyl group and a phenyl group. Becomes sulfide, and if it's oxidized up, it's a methylphenyl sulfoxide. We utilize a different reagent if we want to go all the way. So we can use a methylphenyl sulfide and oxidize all the way up to methylphenyl sulfone, as shown here. There's something additionally important for understanding bonding, bond order, and reactivity patterns. Here's some orbital information background. I had mentioned to you that sulfur compounds can utilize S, P, and D orbitals. When we are now looking at resonance, resonance is such an important concept that we keep on utilizing, applying, and it turns out that this one here and this one here, those are significant resonance contributors. So it has to do with electron density being pushed into the oxygen. Oxygen is a little bit better at stabilizing the negative charge, and you can actually have a Lewis structure like this, where you have 2 negative charges and sulfur with 2 positive charges. And then a reminder that in Orgo 1 you discussed ozonolysis reactions of alkenes, which you have here. This is O3, so your ozone. How do these thiols and sulfides fit in? Well, this is a 2-step procedure. So first step is ozone. Second step is actually now reducing this oxygen-rich compound. So you can see that we have added a total of 3 oxygens, insert 1 oxygen, replace 1 bond with a bridge to oxygen, the other bond with 2 oxygen bridge. And we then need to get rid of 1 oxygen. I wouldn't be too concerned about the mechanism here. And then this ozonide collapses into the 2 carbonyl compounds. And remember that basically what this has to do with, an easy way to just understanding visually what's happening, is I would just redraw the alkene without the double bond. You attach each of the substituents, and now on each side you're putting in an oxygen, and there you are with your 2 products as indicated here. As a result, this dimethyl sulfide becomes a dimethyl sulfoxide, so a net oxygen is transferred over to the sulfur compound. And we'll take a break here.